Everyone. So today, Cagdas is going to tell us about graph-theoretic approach to contextuality. So this is the second branch of our reading seminar part of the the larger seminar, larger quantum computing seminar. Okay, Cagdas, please go ahead.
Okay, I'm Çağdaş, and I will be giving an introduction to this graph-theoretic approach to contextuality. So, starting with my talk, I will define what is a hypergraph. So, definition. So, a hypergraph is defined as its set of vertices and edges, where the H is a set of n vertices. So it's 2 to Vn, and EH is a set of n edges, where an edge is a set which is made up of vertices. It's being a subset of all vertices V with order E. So as I said, the edges are just the subset of all vertices. So then the definition of the graph differs with each edge containing only 2 vertices.
Oh, okay, Cagdas. I have a question. So you're saying EH is a set of n edges? Did you say
No,
n?
not n edges. I'm sorry,
Oh,
m edges. It should be m
okay.
edges.
Could be different, right? Yeah.
Okay, so the graph differs by hypergraph. Just so each edge should contain 2 vertices. For a hypergraph, there is no restriction. So then I will define a contextuality scenario. Okay, so the only difference between contextuality scenario and hypergraph is the union of the elements of all edges must give the set of all vertices. So like the union, the elements, the edges goes to the set of vertices. So formally must equal. So we can't have a vertex which is not contained in any edge. So for example, this is a hypergraph. Maybe I can. But and this is also a hypergraph, but it is not a contextuality scenario because one edge is not contained in I'm sorry, one vertex is not contained in any edge. And for example, this is a graph because, as I said, the edges contain only 2 vertices, and formally connection between graphs is shown like that. So, okay, so in the talk, I will use the terms outcome as vertex and measurement as edge. Okay, so now I will define probabilistic models. Like probabilistic models is probability distributions which we will assign to this contextual scenarios. So probabilistic models. Definition. So let H be a contextual scenario. A probabilistic model on this contextual scenario is an assignment P, which assigns the vertices to the set of probability to each vertex element of set of vertices. So there's a restriction. So the sum of all probability assignments in an edge must be equal to 1. Okay. So, and the set of all probabilistic models on H is denoted as GH. So, is there any questions about these definitions? Guess not. So I will give an example.
Okay, yeah, I was going to say,
Huh.
give me an example would be possible.
Okay. So let's take this contextual scenario. There's 3 vertices, V1, V2, and V3, and the edges are like that. So if we try to assign a probabilistic model to this contextual scenario, so as I said, the sum of the probability assignments in one edge must be equal to 1. So let's write those conditions. So P V1 plus P V2 is 1. P V1 plus P V3 is 1 from this edge, and P V2 plus P V3 equal to 1. So the only solution of this 3 equation is all the probability assignments on the edges, no, vertices must equal to 1 over 2. So there's only one probabilistic model which we can assign to this contextual scenario. Also,
Can you go up to the definition real quick? I just wanted to,
the probabilistic models.
uh, yes, okay, I see. Okay, thank you. I just wanted to see something.
Okay. So also, not all contextual scenarios have a valid probabilistic model. For example, for this triangle scenario, if you take 3 of those triangle scenarios, this, and let me copy those. And let's connect those 3 edges with, no, vertices with this edge. So we found that for every vertex, the probability assignment is 1 over 2. But if we assign this 1 over 2 probabilities for this red edge, the sum of the probabilities equals to 3 over 2, which is not a valid probabilistic model because it violates this restriction. Therefore, not all contextual scenarios have a valid probabilistic model. So I will give another example, a Bell scenario for one party. So let's say there is vertices and there is k edges. So it is a Bell scenario for one party. It's not very interesting case, but it is like each measurement. So none of the measurements shares same outcomes, and there's k measurements, and each measurement can have m outcomes. So this is a Bell scenario. So I can define for as an example of a probabilistic models a deterministic model. So a probabilistic model is deterministic.
Sorry, Çağdaş, in the example above, I just missed it. So this is one. Okay, so this is one party you said, right?
Yes, one party
Okay, sorry.
is deterministic if all the probability assignments are either 0 or 1 for all vertices. Then we can define a classical probabilistic scenario. So a probabilistic model is classical if it is convex combination of deterministic ones. So this definition makes sense because as the name gives itself, a deterministic model. Yeah, if something is deterministic, we know this with certainty that one of the outcomes will be measured with certainty. Then and other possible outcomes we should not measure those. A deterministic probability distribution is something like that, and classical. So like historically, a classical thinking of those probabilistic models is like there should be a hidden variable model that can predict all of the measurement outcomes. And the classical thinking is that we have no information about those models. Therefore, all deterministic models can be true with some probability is a classical way of thinking those probability distributions. So I interpret this deterministic and classicality like that. But if you have another comment about this, you can correct me. So okay, I will be talking about products of contextual scenarios, but is there any questions? Okay. So products of contextuality scenarios. So we want to take product of contextual scenarios because we want to understand how to combine two scenarios or more than two scenarios into a joint one. So quantum mechanically, the tensor product makes this job for us. But for this graph theoretic scenario, we want to the graph theoretic approach. We want to combine two scenarios into a one joint scenario to understand those scenarios. So I will define a direct product. So let J and HB be contextuality scenarios. The direct product is the scenario HA cross HB with the vertices are the Cartesian product of those two scenarios vertices, and edges are the Cartesian product of the edges. So unfortunately, direct product does not give physically realizable probabilistic models always. In order to have a probabilistic model physically realizable, there is a restriction of the probabilistic model, and comes from like the outcome of one party's measurement should not be dependent on other party's choice of measurement. So this condition is called no signaling property. So I will give the definition of it. So probabilistic model P in set of all probabilistic models of this joint probabilistic model is no signaling if condition N all V in each A and so it's basically saying that if a vertex in the first scenario is so we taking the Cartesian product, and if the one party's outcome is contained in two other edges, the sum should be equal. So there's a second for the other. So I can give an example in a scenario. Okay, so what those two conditions are saying is that so if I sum up all those probabilities with respect to W in edges, we got the probability of V in one party's measurement, because this means that V and W both are measured, and if I sum those measurements with respect to W's, I will get the probability of measuring V. And we are saying that if we are saying that for two edges, so the choice of the summing in the second party's measurement should not be affecting the first party's probability. So let me give a direct product example. Those they
I have a
can.
question. Sorry, Cagdas. When you compare A and B, can I see?
Mm.
Isn't there something wrong in the A? B seems to be quite similar.
The
So you're
uh,
running over. Oh, sorry. This is V, right? V and
yes.
so you're running over W, but then the oh, I see. I thought it was U and W, but it's both
No.
U second coordinate, right?
Yeah.
Okay.
So I will give a direct product example to clarify things because visually it makes more sense. So let's say we have a contextual scenario like that. And let's give numbers V0, V1, V2. So, and let's give numbers to edges. So let's say that this is T and we want to compute the direct product T with itself. So if we take the Cartesian product of the edges, we will get 9 edge, no, not edges, the vertices. We will get 9 vertices. So, and if I want to label them, let's label 02, 10V, 11, 12. Yes, then so those are the set of the Cartesian product of vertices. So if when we take the Cartesian product of the edges, for example, taking the E1 with E1, so the Cartesian product of the elements of E1 cross E1 are those vertices. So we can label it like that. And E1 cross E2 must be those because it means that um, the first party is measuring E1 edge. So we labeled the first label as the first party's outcomes. So the first one must be measuring V0 or V1, and the second one must be measuring V1 or V2. And with the same rule, we can label this edge like that, and no signaling condition in those is like, so when we sum those three, or let me, so those three vertices, we must get the probability of Alice getting 0 because uh, in here Bob measured 0, in here Bob measured 1, in here Bob measured 2. So those are the all of the measurements that Bob can perform, and the sum of those three must give the probability of Alice measuring 0. And the choice of the measurement of the Bob should not affect the choice of the probability of Alice getting 0. So how can we see it in other parts? For example, did I make something wrong? Because so no, the 0 vertex not contained in any joint measurement. So we should look at the
Sorry,
uh,
Chadash, I
no,
want to ask
it,
something. It's not that the condition. Can you go up again to the condition above? Yeah. So yeah. So it's not like V00 plus V01, it's equal to V01 plus V02, or I'm wrong? Because
Hmm.
because this is two, like 0, 1 and 1, 2 is different edges. Yeah. It's like, it's not, this is the condition one, like for example, I didn't understand what you say, why you say is the sum of V00, V01, V02 is one.
So it represents the Alice measuring 0 in her measurement. But
But
like
you, but it's not a edge because you're running over all the edges. What I see in the right in your condition, in your conditions A and B.
yes, yes.
Yes.
But the okay, okay. I understand what you are mean. So I got confused in summing those three because V0 is not any other edge. So okay. Uh, so the V1 must be
Uh, am
this,
I wrong in thinking that that's
so
the
those
exact
Yeah,
two.
problem?
exactly. Like for example, this is equal to this. Yeah, the sum. Yeah, this is what
Yeah.
I'm thinking. Maybe
You
the
would like
condition
for
and
that
also.
sum to be one, but you can't have it be one because they're not in the same hyperedge.
Yes, yes. So yes, those three are not in the same hyperedge. So those and those should be equal to.
Equal. Yeah, yeah. So now we
Yeah.
understand the condition.
Okay,
Yes.
I think I mismarked with those three. So yes, this or for example this or the sum of those two and the sum of those two must be equal. But as I said, the direct product not always gives a scenario that respects the non-signaling conditions. So this probability assignment, for example, a deterministic assignment, does not respect non-signaling conditions because Alice knows the measurement choice of Bob with certainty. For example, if Bob chooses the second measurement, the Alice will measure the zero outcome with certainty. But if they both chose the first measurement, Alice cannot measure the zeroth outcome. So this does not respect the non-signaling condition. So I'm sorry, I think I marked those three when I try to explain non-signaling conditions. But yeah, you are right. We are summing over the edges.
Sorry, Cagdas, can I see the top part where you define the product of maybe a bit more. Yeah, here. Okay. So I see. The edges are products of the two. So that's how you mark the new hyperedges, I guess that's.
Yes, yes. The
So
product.
when you I guess when you run over in the summation formula, when you run over something, these E and E prime uh are the edges of one of the contexts, say
Yes.
Bob or Alice, right? Okay. Well, let me see. So again, could you go over which of the two are the same when you do an example on this? Uh,
So this scenario.
yeah. So I guess you can take, say we're marginalizing to Alice.
Yes.
Is that
And
the first party? I guess the Alice is the second party in your
no,
pairs
the
in either A and B. I guess that's which
the
one did you intend?
first is Alice.
Okay.
And in this configuration, the horizontal ones corresponds to the sum of horizontal ones corresponds to the Alice's probabilities. So this two, the sum of those must be equal to sum of those in order to have the non-signaling condition. Because the sum of in here, Alice measures the first her first measurement, and in here Alice also measures the first stage first measurement, but the only difference is that Bob changes his measurement. So Alice should not suspect those change in her probability distribution. Therefore, those two will give the measurement, the probability of measuring 0 in Alice, and those two should equal, because if they are not, Alice, without changing her measurement, can sense what Bob measured, what Bob chose as a measurement.
Okay, okay.
Okay. So any questions about this? So I'm sorry, when I mark at first, when I mark those vertices, I mark them wrong, but the sum should be made with respect to the hyperedges.
Yeah, I guess it's a bit confusing. I mean, I think the marginalization condition, at least to me, looks more natural in the shift theoretic one, because I mean, if
Yeah.
you go to the summation again, yeah, it's a bit. If you go up a bit more, I guess the first thing one needs to fix is the vertex on one of the coordinates, and I guess when you sum of the take the sum of v0, 0, v01 and v01, v0, 02, I guess the vertex you're fixing. In this case is V0,
Yes.
I guess. So
Yes.
yeah,
In this
like in
example,
your
I'm looking
formula, there's this
at
fixed vertex.
0. Yeah, I think it's a bit confusing comparing to, like, for
Okay,
simplicial
okay.
distributions, those gluing lemmas makes the confusion less. But yeah, you should sum with respect to hyperedges. So as I said, in this example, for example, we solve that direct product does not necessarily give this non-signaling conditions. So but we have another product which is called Foulis-Randal product.
Sorry again, Cagdas. So the failure is because in the top part, 0 plus 0 is not equal to 0 plus 1. Is that why we
Yes,
fail? Okay. Oh.
because Alice knows with certainty what Bob chose as a measurement in this scenario. So we have the Foulis-Randal product, shortly FR product. Is the scenario HA cross tensor with the vertices are still the Cartesian product of two scenarios. For the edges, we have the union of those set of edges where this is defined as, so the definition is a bit messy to understand, but I will clarify. So it is a union, and for if we look at the element of an element of the union, so for A to B, we will choose a element of a specific edge of the first scenario cross, then we have a function which so this EA is an element of an edge in the first scenario, and this function assigns an element in an edge, so it assigns a vertex to an edge in the second scenario. So it's basically saying, like, so physically thinking is Alice doing a measurement, and it's so she obtains one outcome. because we say that the vertex and the outcome are the same thing. So she gets an outcome and communicates with Bob. And Bob then, from the communication, Bob chooses a measurement depending on the measurement outcome of the Alice. So this function says something like that. So we are taking an vertex in the first party, Alice, and from this measurement outcome, we will assign an edge, a measurement to a Bob in this joint measurement scenario. And the same applies for, so it's the definition. Same applies for Bob communicating to Alice, his outcome. Okay. So we are choosing those because it gives the non-signaling conditions automatically, and they are physically realizable scenarios. So it can be a measurement scenario such that Alice communicating her measurement to Bob, and Bob choosing a measurement in his side. And I think there's some like quantum games, or I saw in some papers like Alice communicating her measurement to Bob, and Bob tries to guess something, but those scenarios are, I think, realizable, and they have some value in some different branches of quantum foundations and quantum information. So I want to give an example of this product, which we can see how this product gives the non-signaling conditions. So let's say the two parties have two measurement choice with two outcomes. So I will label this measurement as 0, and I will label the outcomes as 0 and 1. And I will label this measurement as 1. So let's say this is the Alice's two binary measurements. So measurements. So it's like when I define a Bell scenario for one party, if you look at it, it is m equals to k equals 2 for Alice. There is two measurement, and each measurement has only two outcome. And let's say the same applies for Bob. So Bob has two measurements, and they are two binary measurements. So no measurement shares same outcome, and two parties has the same measurements actually. So I want to make a comment. So the union of those two measurements actually gives the direct product also. So we can think of the direct product as the Bob's measurement choice does not depend on the measurement outcome of the Alice. So Alice communicates her outcome to Bob, but Bob measures the same measurement independent of the outcome. So let's take the direct product first. And I think when we take the direct product, what I am saying will be more clear. So we first taking the Cartesian product. And it is an edge. Let me copy this edge 4 times. And change the labeling. So as we can see, for each edge, we see that no matter what Alice measures, the measurement choice of the Bob does not change. So it is a valid result in this definition because it does not insist that the Bob should how can I say, Bob should change his measurement according to the measurement outcome of the Alice. And actually the elements which is in this set and this set. So if if an edge is an element of this set and this set, it corresponds to the direct product of those two scenarios. So now we will take.
Cagdas, I have a question. So can we see these four contexts as is that what you're saying? So we can see these four contexts as also as contexts in the Foulis-Randal product?
Yes.
So the
And
f function, what would be the f function in this case?
so f function is a constant function
Constant
in this
function,
case.
yeah.
Now I will take the other product. So let me copy this. So this is the direct product. And so now we will take the Bob's measurement choice, depends on the Alice outcome. So let's say that Bob measures his zeroth measurement if Alice measures the zero, and he measures the one measurement if Alice measures one. So it corresponds to this hyperedge because Bob measuring the zero measurement, so the second one is Bob. If and only if Alice measuring the zero, and the converse happens for if Alice measuring one, Bob measures the one measurement in his choice of measurements. So this is the Bob's measurement choice depending on the Alice's outcome, and this is also same, but this the converse scenario. Bob chooses the measurement zero if Alice measures one, and the converse if Alice measures zero, Bob will measure one. So these 1 zeros are mixing, but if there's a question, you can ask. And so those are the edges with same logic. So for example, in here, missed this. Okay, so in here we can see it. So in Alice's first measurement, if Alice measures 0 in her first measurement, Bob will measure his first measurement, no, 0th measurement, and the converse is like that. So is there any question of constructing this Bob's measurement choice depends on Alice's outcome?
Yeah. So okay, I think I got the first two. So
Mhm.
here we have the function from Alice to Bob, right?
Yes.
But the other two, is it is still the function from Alice to Bob, or is it
Yes, it is
still
still
Alice
because
zero? So we have
so
the zero
hmm,
outcome for Alice
yes,
is mapped to which
the
measurement for Bob? Is the zero measurement for Bob?
yes, the zero outcome in Alice's one measurement will be mapped to the zero measurement of the Bob, and the converse is this
One is mapped to one, one is
yes.
mapped to one. How is this different from one is mapped to one?
The difference is so difference between those two hyperages and those two hyperages is that Alice in those two Alice is measuring her zero measurement, and in those two Alice is measuring
Oh,
her one measurement.
okay. Oh, I see. Okay.
Okay. So
Yeah.
Bob's measurement choice depends on Alice outcome. And so this is the function this. So those edges corresponds to this edge assignment. So then we will do this. By the way, this direct product is contained in both this set and this set. Now I will do the bobs. Let me copy all of those. So in here, now let me get different color, maybe purple. Okay. So in here, Bob communicating his measurements to Alice, and Alice changing her choice of measurement. So for example, this. So in here, Bob is measuring his zero measurement, and Alice chooses her zero measurement if Bob measures zero, and the converse is for one. So it is the function in here. It is the function of b is 0, then fb is the zero edge. And if b is 1, fb is 1 for Bob's zero measurement. And so this is the converse. So in here, Bob still measures his zero measurement, and Alice chooses her one measurement if Bob measures zero, and the converse. So with the same logic, it gives this hyperedge and that hyperedge. So this is the Alice's measurement choice depends on Bob's measurements. Oh, measurement outcome. So is there any question about this product? Okay, so now the combination will give us the all measurements. So I will try to copy all of those into a joint one. So let me copy. So I am taking all of the hyperedges that is generated. I am lucky day will coincide, yes. Okay, so we can see that so those are the result of the total product, and we can see this gives the non-signaling conditions. So what non-signaling will say in here? So let's look at this two measurements, so two outcomes. So in here, Alice's choice is her zero measurement, and Bob's choice of the measurement is also zero. And if we look at those two, in both outcome, Alice measured the zero. So the sum must be must equal to the probability of Alice measuring zero, because in those two, Bob measured zero and Bob measured one. So for this joint probability, those two sums should give the probability of Alice measuring zero. So in here, the only difference is Bob changed his measurement choice. So we want the sum of those two and sum of those two equal. So in here, when we look at it, so for because of this red hyperedge, the sum of those two is 1 minus sum of those two. And from direct product, we have this blue hyperedge, and it is saying that those two is also equal to 1 minus sum of those two. Therefore, this and this, the sum of those two and the sum of those two, they are both equal to 1 minus sum of those two measurement. Therefore, non-signaling conditions are satisfied. So we can check all for all of those marginalization, but as you can see, this product gives those non-signaling conditions. So I will ask, is there any question?
No, I think that's at least for me, I think that's quite clear that it's a very weird way of encoding the non-signaling conditions in these
Yeah.
products. But I think that was that's the figure 7, right? From the paper.
Yeah, the same figure.
Yeah.
They
Okay.
also rearranged the vertices, but
Okay. Yeah. So I guess the claim is that we get all. So there are 4 plus 4 hyperedges here, and it matches with the 4 non-signaling conditions of CHSH. So that's the CHSH, right? And we have 4
yes.
normalization. That would make 8. Yes, and we can
Yes.
find all of them. Yeah, I guess one interesting thing we noticed at some point with Moses is that you can also do the twisted version here if you choose the hyperedges correctly. So apparently this is quite general. And I think I have a question. So I think it's about one of the first examples which doesn't admit any probability distribution. So I guess I thought you can go back and forth between the graph theoretic approach and the sheaf theoretic approach. I guess there's something like that in the appendix. But maybe I guess for the scenario you have shown these three triangles, and then there's a middle triangle connecting all of them. So it doesn't admit any probability distribution. I don't think there is a this sheaf theoretic formulation of that. So because or simplicial distribution formulation, because you would always get a distribution. I don't know how to formulate that. Can that be formulated? I don't think so. Because I mean the space, the set of distributions is never empty in simplicial distributions. So the graph theoretic formulation looks more general. Maybe those cases are a bit pathological, but anyways, I think that's this
Yeah, because
weird
yes, there is.
example is interesting. Yeah.
Yeah, so you're talking about this example, right? For example, this does not admit
Yeah,
any
exactly.
probability. Yeah,
Doesn't admit anything. So
yeah, I think it's all it's interesting because I didn't see any thing in similar thing like in simplicial distributions.
yeah.
So I have 3 minutes, and I I didn't talk about the non-orthogonality graphs. I thought that if I have enough time, I can talk about it, but I think it's 6:30, so should I end it here or maybe just giving the basic definitions?
I guess yeah. So we discussed this point with you, right? I guess if
Mm-hmm.
it's going to be used later, I guess it can be defined later. Since yeah, just giving the definition. I think this is a nice cutoff at this point.
Okay.
So okay, any questions for Çağdaş?